Hello everyone, and welcome to another episode of Code Emporium, where we're going to talk about the power of decision trees for causality. In my last two videos, we tackled causal inference. The first video kind of explored to answer the question, does the treatment actually cause people to get better? And the other video answers the question, how much does the treatment affect a specific person? And we did this using traditional machine learning models, but in this video, we're going to answer the same question using decision trees. So decision trees. These are trees used to make decisions. Each tree has internal nodes that have children and external nodes or leaf nodes that have no children. Let's illustrate this with a medical example. The flu is a problem for the world, and I developed an elixir that I think should cure the flu. But before releasing it to the world, I want to test if this elixir works. And here's data for 6 people who came to me with the flu. For each person, we're tracking their gender, whether they were treated with the elixir, their age, which is a continuous variable, and finally, if they were cured. Let's say we have this decision tree to determine if a given patient will be cured. Let's take the first sample, a J, and see how this works. So a J is going to be passed to the root of the node at the top. His age is checked to determine if it's above 30. It's not. So we go to the left leaf node, and this indicates that a J will be cured. It's a prediction. Now let's take our second patient, Sydney. She's passed into the root node at the top. Age is checked to see if it's above 30. It is above 30, so we go to the right child. And this is another internal node where we check if the person is treated with the elixir. They were not. And we predict that this person will not be cured. In a similar way, we can make decisions about whether a person will be cured or not by passing them down this tree and seeing which leaf they end up in. So this is pretty cool, but how exactly did we build this tree? The leaf nodes should be one of two outcomes. Yes, this person will be cured. Or, no, this person won't be cured. The internal nodes can be based on one of 3 variables: gender, whether the person was treated with the elixir, or the age. And the goal here is to choose internal nodes that can best split the yeses from the nos. Let's start with gender as a potential internal split node. If we pass all the patients into this node, we'll end up with 2 yeses and 1 no on the left child, and then we'll end up with 2 yeses and 1 no on the right child. Instead, what if we started with whether the person received the treatment or not as the root? If we pass in all the patients to this node, we'll end up with 4 treated individuals on the left, 2 of whom were cured and 2 were not, and we'll end up with 2 cured individuals on the right. So which split is better? And we can quantify this with the Gini index. So Gini index is going to be 1 minus the probability of yes square minus the probability of no square. Gini index is a measure of impurity. Lower the value, better is the split, subject to overfitting. The Gini index of a split is the weighted average of the Gini index of each child node, where the weight is going to be the total proportion of samples that are in that child node. This might be a little weird to understand at first, but let's walk through this by calculating the Gini index for the gender split and then the treatment split. Before we move on, if you do like what you're hearing right now and you want to know more, please do give this video a like and also subscribe and share it with people that you know, because it would really mean a lot to me. So let's consider the gender split. the Gini index of the left node is 1 minus the probability of yes squared minus the probability of no squared. So in the left node, we had 2 yeses and 1 no. So the probability of yes is going to be 2 on 3, where 3 is the total number of samples in the left node. And similarly, the probability of no is going to be 1 on 3, since there were 3 people in the node, of which only 1 did not cure. Substituting these values, we get the Gini index of the left node as 0.44. And since the situation is exactly the same for the right node, we also get the Gini index as 0.44 for the right node. Now, to compute the total Gini index, we take the weighted average of the Gini indices of the left node and the right node. And here, the weight of the left node is going to be 3 on 6, because there were 6 total participants, 3 of which went to the left node. And the same argument is made for the right node. There were 6 participants, 3 of which went to the right node. And substituting these values and taking the weighted average, we get the final Gini index as 0.44. Now let's compute the Gini index for the treatment split. So on the left node, we saw that there were 4 treated individuals that went to the left, 2 of whom were cured and 2 were not. So the probability of yes in the left node is 2 on 4, and the probability of no in the left node was also 2 on 4. And substituting these values, we get the Gini index of the left node as 0.5. Now let's do the Gini index of the right node. Now for the right node, there were 2 individuals that went there who were eventually cured. So the probability of yes is going to be 2 on 2, and the probability of no is, 0 on 2. And substituting these values, we get the Gini index of the right node as 0. Now, since we had 4 individuals who went to the left node out of 6, that is going to be the weight of the left node, and 2 people out of 6 went to the right node, so 2 on 6 is going to be the weight for the right node. And substituting these values, we get the total Gini index for the treatment node as 0.33. From these calculations, we see the treatment split is the better split since it has a lower Gini index. Let's compare this now to the age split. The split for age isn't apparent, but we can get splits with a few simple steps. So we take the age of all individuals, sort those ages in ascending order, determine the average age of subsequent entries, and use each of these as potential thresholds to determine Gini indices. So let's take the first case. Age is greater than 24.5. If we pass all the patients into this node, we'll end up with 1 yes on the left child and 3 yeses and 2 nos on the right child. We now compute the Gini index of the split. So on the left child, we had 1 yes. This means that the probability of yes is 1 on 1, and the probability of no is 0. And substituting this in our Gini index equation, we get the Gini index of the left node as 0. Now for the right node, there were 3 yeses and 2 nos, so the probability of yes is 3 on 5, and the probability of no is 2 on 5. And using these values, we get the Gini index of the right node as 0.48. And the total Gini index is going to be the weighted average of these 2 values. Since only 1 out of the 6 samples went to the left node, its weight is 1 on 6. And the remaining 5 on 6 went to the right node, so its weight is 5 on 6. And substituting these values, we get the final Gini index of the split as 0.4. And like this, we can compute the Gini index for all other age splits. And I encourage you to walk through these numbers and do the math just to make sure that you're on the same page here and you understand how these Gini indices are constructed. Now, in doing this math, we see that the age is greater than 30 split has the lowest Gini index here. Hence, it is the best split. Let's consider age greater than 30 split and pass our patients here just to see how the children look. We don't need to split the left child since its Gini index is as low as it can go. Now for the right child, we can check gender, treatment, and other age categories as we did to further split this out. If we pass these 3 patients into the treatment node, the left node now has 2 no's and the right node has 1 yes. This is a perfect split, and the Gini index of this split will be 0, so you can stop here. We now assign a yes or no label to each leaf depending on the majority. And we're done. In this case, we had pure nodes, but in practical situations, we would see some impure nodes too. I hope the tree construction here is clear. The decision tree answers the question, determine if this person will be cured given a person's age, gender, and whether they were given the treatment. But what if we want to go a step further? And we want to answer the question, should we give this person the elixir? Answering this question means the tree needs to understand if the treatment causes the flu to go away. And we can answer this by making a few modifications to the tree itself. The leaf nodes should be one of 2 outcomes. Yes, give this person the elixir, and no, don't give this person the elixir. And the internal nodes can be based off of one of 2 variables now, gender and age. And the goal should be to choose internal nodes that can best split the yeses from the nos. For the best split, those treated should behave as different as possible from those who are not treated. If a lot of treated people were cured in a node, then the non-treated people should not have been cured. This way the node will be as pure as possible and we can assign a yes or a no to the node. And we quantify this node purity in this way with a metric called divergence. Larger the divergence, more pure is the node. We want this divergence for a node to be as large as possible. So divergence will be the probability that a person is treated and cured minus the probability that a person is not treated and is still cured. Square of that plus the probability that a person is treated and not cured minus the probability that a person is not treated and doesn't get cured, and the square of this. Let's understand how well this metric works by constructing a new decision tree that answers the question, should we give this patient the treatment? So let's first consider gender as a potential split. If we pass all the samples through the decision node, then on the left node, we get 1 treated person who got better, 1 non-treated person who got better, and 1 non-treated person who did not get better. And on the right node, we get the exact same thing. Let's calculate first the divergence of the left node, and we'll do this 1 term at a time. So the probability that a person is treated and cured is the number of people who got cured divided by the number of people treated in that node. So we have 1 treated person who got better, and the total number of treated people is just 1, so it's 1 over 1. The probability of not treated and cured is the number of people who were not treated and who got better, which is 1, divided by the total number of people who are not treated in that node, which is 2. Now, the probability of a person being treated and not cured is the number of people who were treated and didn't get cured, which is 0. And so it's just 0 over 1 since 1 is the number of people who got treated. And the final term is the probability that a person is not treated and not cured, which is 1, divided by the total number of people not treated in that node, which is 2. And so plugging these values into the formulation, we get a divergence of the left node as 0.5. Now similarly, we also write out the divergence of the right node in the exact same way. And now, like we did before when we were doing the Gini index of the split, the divergence of this split will be the weighted average of the divergence of the left and right nodes, and the weight will be equivalent to, depending on how many samples there were in that split. So in the left node, we have 3 out of the total 6 participants, and in the right node, we also had 3 on 6 of the total participants. And plugging these values in, we finally get a divergence of 0.5 for the split. Now let's consider age as a potential split, and we'll use the thresholds that we determined before, starting with age is greater than 24.5. If we pass all the patients through this decision node, then on the left node, we will end up with 1 non-treated person that got better, and on the right node, we will have 2 treated people who got better, 1 non-treated person who got better, and 2 non-treated people who didn't get better. Now, let's also again compute the divergence of the left node. So the first term, there are no people who got treated, so we'll leave it as 0 here. The next term is the number of non-treated people who got cured, which is going to be 1, divided by the total number of non-treated people in that node, which is 1, hence 1 over 1. Now the third term is going to be 0 because there are no treated people. And the fourth term is going to be the number of non-treated people who didn't get better, which is 0, divided by the total number of non-treated people, which is 1. And plugging these values in, we get a divergence of the left node as 1. Now for the right node, we have a lot more participants here. The first term is the number of treated people who got cured, which is 2, divided by the total number of people who were treated, which is also 2. Hence 2 over 2. The second term is the number of non-treated people who got cured, which is 1, divided by the total number of non-treated people, which is 3. Now the third term is the number of treated people who didn't get cured, which is 0, divided by the total number of treated people, which is 2. And then we have the total number of non-treated people who didn't get cured, which is 2, divided by the total number of non-treated people, that is 3. And substituting these values, we get the divergence of the right node as 0.888. And then computing the weighted average of the left and the right nodes, we get 0.907 as the divergence of the age greater than 24.5 split. So it looks like the divergence of this age split is higher than that of the gender split, and this means that the split of age leads to more pure nodes and is indicative of a better split. And like this, we can compute the divergence for each age split. We notice the highest divergence in the case of age greater than 25.5, and so we make use of this as the split. Looking at the result of this split in the right node, all the treated people got better and the untreated people didn't get better. This is a very pure node where we tell everyone, yes, take the elixir. This is reflected in the divergence that is also maximum for this node. Now in the left node, whether people took the treatment or not, they got better. So we might stop here and assign this leaf with no, don't give them the elixir since they're going to get better anyways. But in reality, we'll have more columns to work off and we would keep building the tree out potentially. And there's definitely way more samples than 6. But I hope you still got an idea of how to construct this tree and compute divergence and understand which split to consider. And now when a new sick person comes to me, I can use this tree to decide whether or not I should give them the elixir, as it will help me identify whether the elixir will actually help them recover, or they can just recover on their own. So cool. As a summary of this video, we talked about decision trees, what they are, how they can be used, and how they are built. We also saw how we can use decision trees to answer deeper questions on causality by changing what the leaf node represents and by changing how we measure node purity. Before we were using the Gini index, and then we later used divergence as a different metric. And we showed how these causal decision trees can also be built. So that's going to do it for this video. Thanks a ton for watching, and there's definitely so much more to causal inference that I have not discussed, and I've discussed in past videos, so please do go watch them. I've linked to some more resources down in the description below. Please be sure to like, subscribe, and I will see you very soon. Bye-bye!